So let's start right now. Good morning, everybody. I'm speaking. I'm from the ATOS Build Company. I'm very glad to welcome all of you to this webinar dedicated to the topics of uh, intelligence artificial accelerations. So for this purpose, we'll have two presentations on this topic. The first one will be from myself, and the second presentations will be more oriented toward software and integrations of AI accelerations to the cloud service. Will be done by Constantina Coglio-Giorgi from ICCS. Afterward, we will have a demo, and at the end, we will have sessions of questions and answers. During our presentations, I will suggest that you submit already your questions, and then we will collect all those questions and answer at the end of the sessions.
Now,
Okay.
can you put your presentation as exactly?
Like that?
Yes, perfect.
Okay, so I will start first with my presentations, which is about the use of hardware accelerations in order to accelerate AI-based applications. I will start with a first slide to talk about our motivations for AI acceleration. So first of all, I would like to make some precisions when I talk about AI acceleration. Some kind of keywords used by many people, but on these keywords, in fact, we are only focusing on the accelerations of artificial neural networks. It is very small subtopics of AI. And maybe it sounds obvious for you already about the reasons why it is necessary to accelerate those artificial neural networks, but it is worth to go through a little bit about all those points in order to, how can I say, to specified again the different constraints and objectives for each part of the neural networks we would like to accelerate for those applications. So first of all, about the evolutions of artificial neural networks. So everybody's understand that it has a lot of evolutions on this kind of modeling in terms of size. That means that there is a larger and deeper models of ANNs. In terms of the computation pattern, there's also some lot of evolutions on the ANNs and different type of ANNs as just reporting here about the feed-forward type of ANNs, recurrent ANNs, and autoencoders, etc. There's a lot of evolutions on those topologies and functionalities of those artificial neural networks. And it results from that there is an exponential increase in computations. That's why we need accelerations of computing in order to provide practical exploitations of those neural networks. But this kind of needs of increase in computations are quite different for different phases of ANNs. For the training phase and for the inference phase, the needs are a little bit different. For example, for the training phase, which deal with pushing batches of training data through the pipeline of network layers. And the main objective is to be performed is about the throughput. And it has as a characteristic that it allows the use of layers of weights to each item of the batch used for the training. And the training algorithms themselves, a different type of algorithms use mostly related to the lessons of gradients algorithms are highly parallelizable. And that's why for the training phase, the accelerations are suitable to use data parallelism and usage of multi-thread hardware like the CPUs and GPUs is quite good for accelerating this phase. For the inference phase of the ANN, which deal with the execution of a single input, maybe in pipeline mode, but a single input through the many layers of the network. The metric, the objectives to target is a little bit different. It is about the latency, it is about accuracy, it is about storage footprint, etc. And obviously, the inference operations involve the use of highly parallelizable operations at each layers of the processing. And it offers also fewer opportunities to use data as for the training phase. And it also requires, in order to accelerate this processing, to reduce the cost of data movement. So at the end, when we combine all those objectives, there is objectives about the throughput, about the latency for the different phase of the ANN processings, but also we have to take into account also other kind of objectives which are common for the both phase, which is memory usage and also energy, depending on which kind of architectures those ANNs are used. Either it is much more, how can I say, critical as objective for the usage of inference, for example, in edge computing, for example, in terms of energy. So after saying that about the motivations to work on the accelerations of AI algorithms, we like to say that for the hardware used for the accelerations of AI applications, hardware does not come alone, but it comes together with layers of software in order to be able to support the usage of those hardware. So it is a pair of software and hardware together, which is used in order to accelerate AI applications. For the software part, which are the main characteristic features used for software in order to accelerate those AI applications. First of all, the first point is to improve the algorithms you have defined. For example, using some kind of standard framework like TensorFlow, PyTorch, etc. So the algorithm, as it is defined, has to be improved afterward. In which kind of for which kind of criterions? For the graph structure itself can be optimized horizontally or vertically by making some kind of fusions between different layers, for example. It also can improve by pruning some kind of operations which can go down some kind of threshold of significant values can be eliminated. So, and also the exploitations of sparseness of the matrices used in the computations of those neural networks. Obviously, those matrices sometimes for the pruning and also for some kind of values of weights can be considered as rather sparse. And then the organizations of those matrices will help to reduce a lot of the amount of memories, for example. Simplification of expression is some kind of very classical. Quantization of bit width in order to reduce the precisions while reducing the amount of memory while maintaining some kind of precisions is another kind of objectives in such an algorithm improvements to accelerate the computation. So automatic precision optimizations also are part of those actions can be done in order to improve algorithm. Matrix decompositions is another actions taken into for those kind of improvement. That means that the matrix itself can be decomposed into submatrices, to blocks, which can be used in order to perform some kind of partial operations over the multiplications with another vectors, for example. It is some kind of very classical too. And the purpose of doing that is that we can reuse some of those sub-blocks more frequently, and we can locate it more in memories which is closer to the processing units, so minimizing the movement of data, as I been said in the previous slide about the accelerations for inference. data compressions using different techniques, that's entropy coding, for example, or memory reuse also help to reduce the amount of that of memories used for this purpose. So this is the first, how can I say, objectives of the software, which are used together with the hardware part. The other characteristic of the software are about the implementations. That means that we have to be able to interface with existing standard frameworks like TensorFlow, PyTorch, etc., or supporting some kind of standard intermediate form as defined in order to be able to be independent from those different frameworks, and also to support, if those frameworks, existing frameworks, does not support already, to be able to support some standard programming models like OpenCL, for example, and particularly for some acceleration technologies like Fpga, for example, which are not yet very well supported by standard frameworks. In terms of implementation of the software, another criterion is about optimization of compilations. And we have a piece of models. How can we compile it into a very specific piece of hardware? So we have to take into account the kit called locality of data in order to optimize the access to the cache, the reuse of memories, and also to export as much as possible in case quality is existing, for example, using CPUs, for example, the different properties of memory consistency, currencies, for example, in order to avoid the bus contention, etc. So examples of this kind of software accelerations which go together or which complement the hardware accelerations, there are some general purpose software like NC, Intel and Graph, which is working together with Openvino. We'll go back to this point a little bit later as an example to illustrate this part. There are also some software dedicated to some hardware like NVIDIA Tensor RT, Habana Synapse AI, for example. We also go back to a little bit to this point a little bit later for illustration. So, as said before, this is an example of a layout of between level code general purpose software, which can be used together with some a large family of hardware accelerators for AI. I'm talking about Intel Openvino SDK, which is a layout of software which allows to support a large range of accelerators from Intel, from CPUs to VPUs, etc., and GPUs also, but GPUs from Intel, not general purpose NVIDIA GPUs, and also provide some optimized code for computer vision standard like OpenCV, OpenCL. So as it is illustrated in this figure in here, we start from a pre-trained models obtained from standard frameworks, for example. We go into some model optimizers, which produce some intermediate representations, and then it can go through some inference engine, which can be mapped and work onto a large range of different hardware accelerators, from CPU, VPUs, to dedicate the GPUs from Intel. So here are the different components of the Openvino. I will not detail it too much. So after talking about the software, let's talk a little bit now about the hardware itself. So there is the hardware used in order to accelerate AI. I will classify it into two different families. The families of what we call general purpose hardware used for acceleration of AI. Well, why do I call it general purpose? Due to the fact that this kind of acceleration can be used for other purpose than only for AI acceleration. It can be used for simulation, for other applications, for engineering applications, not only for AI. So that's why I call it general purpose hardware. And it includes traditional multi-core CPUs, for example multi-core from Intel Xeon 3 processors, but also GPUs, which is very classical today, usage of the GPUs, for example, from NVIDIA in order to accelerate AI applications. Currently, when we look at the different, in the literature, different implementations of deep learning algorithms, most of the times the GPUs are the most used technologies for this purpose. And they also dedicate hardware like NVIDIA LGX2, for example, and software to support those frameworks from NVIDIA. And it should be said that somehow today, based on some publications of the LM benchmark, for example, GPU sounds to be very efficient implementations hardware to accelerate AI. Besides the GPUs, we have also fine-grained parallelism FPGA, which is also general purpose hardware accelerators, but it is much less integrated with frameworks. So today, the most used approach to this kind of accelerators either to use high-level synthesis, direct high-level synthesis, using either the hardware description language or OpenCL standard, for example. And the implementations on the FPGA itself can either be done directly, that means synthesizing all the stuff directly on the FPGAs, or synthesizing it on a predefined architectures of networks of processing elements already implemented on the FPGA. That means that the synthesis in this case is much more a compilation than the synthesis. So here are the main technologies for general purpose hardware accelerations. Beside those technologies, we have also some specific hardware which use highly parallel architectures, which can be classified into three parts. There is temporal architectures like SIMD, spatial architectures in the case of data flow, for example, which use data reuse and also interconnections of different processing elements on those architectures, and arrays of VLIW processors. I will illustrate this a little bit later. And today, when we look at what is existing on the market, for example, we can find out a lot of products, more than 100 products, and particularly a lot of them coming from the academic part, from universities. So if we focus only on industrial products, really real products who can be used in industrial context, for example, let's say there is some 10 of product, that's all. And here are some examples I put in here. Google TPUs, Habana, Goya for experience, Gaudi for the training part, for example, GOC TSP or GAFCOR IPU, for example. So here are the main industrial products existing in the context of many other processors. Most of them are some kind of specific implementations on general purpose technologies like GPUs, for example. So in order to illustrate this kind of hardware, I use as example the Habana Goya, which is a specific ASIC used for the accelerations of inference, so on the inference part of the neural networks. It is not really done within the Evolve project, it is beyond the Evolve project, but I use it in order to illustrate one of the architectures said previously, that is an array of VIW processors. Because in these chips, we have three different engines, the TPC, the GMM, and the DMA. DMA for access to the memory, GMM for some operations on matrices, which is shared between the different TPC, and TPCs are tensor processor cores, which is some kind of VLIW SMD vector cores, the C programmable processor. Each TPC has a local memories, which can communicate with the share memories, and from the share memories, we can access to the outside worlds through a DMA. So here are some kind of, I'll say generic, but something which illustrated the kind of accelerations engines can be used for the different part. And another point important is that this kind of accelerators support different precision data type from 40.32 to unsigned integers 8 bits. So I will go now to the benchmark in order to illustrate some of the results we have obtained on some of those acceleration technologies, and in order to say some things about those acceleration technologies, how we can compare one against the other. In the first table in here, we use 3 neural networks, a very classical one, AlexNet with 8 layers, which is 16 layers, or in 50, at least 50 layers. And we perform this kind of inference through different usage of combinations of software and hardware accelerations as said previously. So we use Openvino on CPU, Openvino on GPUs. Well, once again, GPUs, Intel GPUs, embedded Intel GPUs. We use TensorFlow directly on GPU, different GPUs, K20, P40, and most recently V100. And we also program those neural networks using FPGAs, directly using OpenCL. And we use for this purpose the ARIA 10s from Intel and Stratix 10 also from Intel. And you can see that the best result obtained for each of those networks are different from one to another acceleration technologies. The GPUs of V100 sound to be good for large neural networks, for VG16 or SNES50, for example. But for small one, sound that the Openvino on GPUs from Intel is rather good. So what I would like to say is that when performing the benchmark, has taken into account very cautiously the usage of different neural networks, which can react differently on different acceleration technologies. We cannot compute on using only one neural network, because each neural network has its own characteristic. ResNet is something which is quite different from G16, for example, quite different from another kind of neural network. So it's very cautious in order to use those neural networks for the benchmarking. The second table is about the training. In terms, the results are in terms of minutes for the training of 100 epochs. And once again, we use the same kind of neural networks and for the training on using different accelerators, varying from CPU, GPUs, using TensorFlow. Another benchmark put in here, in order to set 2-3 points about the variations of social benchmark. So on the right side, when you use, first of all, once again, I would like to insist in the fact that when you use the benchmark obtained from one neural networks are quite different in terms of variations to another. For example, for VGG16, the ResNet 50, for example, you can see that the curve which represent the throughput using different precisions, varying from int8, int16 to FP32, quite different. How can I say the shape of the curve, and this is done using some accelerator, hardware accelerators. I won't name which one because we are under NDA, so we cannot give the name of the kind of accelerators. But you can see that the variations of those curves are quite different from one to another, and there is some kind of inflections when we give it. We perform the inference on different sides of batch. In the x-axis is the size of the batch, and you see that there is some kind of change of the evolutions according to the size of the batch. What does that mean? That there is an impact when you increase the size of the batch, the impact on the memories, on the movement of data from memories to memories becomes more and more critical in terms of influence on the performance. So we have to take into account um, those kind of criterions. At the beginning, it can increase a lot due to the fact that when the batch size is rather small, it can help to, how can I say, to reduce a little bit some parts of the batch size. But when it exceeds some kind of threshold, it can provoke some kind of overhead data movement from memory to memories, and which can have a big impact on the performance. In terms of precision, for example, on the left-hand side, when you compare again NVIDIA GPU's precision for FP32, for example, we can see that obviously there is a variations in terms of precisions when you use int 8 or int 16. It is significant, but there is not that much variations, about 75.66% compared to 75.7%, for example, between int 16 and FP32. So most of the time, when you perform inference, most of the time we reduce this kind of precisions in order to gain a lot in terms of memory. Parallel inference, I won't enter too much into the, how can I say, the analysis of this. Once again, in this kind of results reporting here, what we like to show is that there is a lot of influence when we try to perform inference in parallel on different instances at the same time, and it can have influence and to slow down the performance due to the fact that there is some kind of bottlenecks in the memories, in the usage of memories. And the main point I would like to point out in here is that there is usage of memories can have a big impact on the performance of the accelerators. So I come now to the conclusion. I'm sorry, I'm a little bit late. So today, there is no single, from my point of view, no single hardware solutions, accelerators, you can have work with every kind of usage. Even if there's some trends according to the publishings of the ML perps, that some technology sounds to work well, but depending on the specificity of your neural networks, there is no on one hardware solutions which can give the best results for all different kind of neural networks. Of course, it depends on the model type and programmabilities, target the throughput and latency and cost for that, depending on the objective we are targeting, and the usage of the compilers and runtime toolchain, which are the criterions in order for selections of such solutions. And for the benchmarking, when we perform benchmarking, there's also a lot of difficulties in terms of accessibilities, reliabilities, exhaustiveness, and fairness, because we have to access to maybe some technologies in order for the benchmarking on the cloud. And there is a lot of constraints don't allow you to perform all the kind of measurements you want to do. And afterward, the selection criteria we have defined within the Evolve for the futures. There is technical criteria about the precision, performance, energy, for example, obviously, but also take into account also the cost, which includes the porting efforts and the assistance in terms of debugging. But debugging is a very important point also, because at first when you use the first technology, sometimes you fall into some very where the solutions. So we have to analyze and understand why obtain so bad performance, for example. And obviously, profiling is another kind of features we would like to have in order to help in the usage selections of an acceleration technologies. And obviously, potential evolutions. That means that we start with a version of technologies, like to understand how does it evolve in the future. So here are somehow all I would like to say about our experiences in using hardware accelerations for AI in the frameworks of the Evolve project. I have finished my presentations, and I suggest if you have any questions, submit it while I leave the floor and invite Konstantina to make her presentation for the next presentation about software in the cloud service. Go ahead, Konstantina, please.
Okay, thank you, Nam. So hello everyone from my side. My name is Konstantina, and I also work on the Evolve project on the ICCS team. I will start sharing my screen and begin with the presentation. So in this part of the webinar, we will explain how the acceleration capabilities described previously can be leveraged from Evolve users within high-level software technologies. As mentioned before by Nam, Evolve delivers a state-of-the-art platform with access to heterogeneous resources for acceleration of applications such as GPUs and FPGAs. Thanks to the capabilities of these resources, the platform is a very promising one for accelerating applications from the machine learning domain, which combine both big data and HPC characteristics. The variety and the versatility of the features enable the use of different resources for acceleration based on the needs of each application. For example, for high throughput, small size inference tasks, the best solution for acceleration would be to use the FPGA, the GPUs connected to the platform. Whereas for single request inference tasks on large inputs, FPGAs can also be leveraged. Another advantage of the Evolve platform is that it offers the convenience to execute an end-to-end machine learning workflow on the same node of the cluster. Starting from the ETL tasks and moving on to training and inference tasks, users can execute all stages of their machine learning workflow on the same node without having to suffer a huge overhead over transferring a big amount of data. Evolve platform provides transparent use of the accelerators through popular software frameworks that are used broadly for running machine learning and big data applications. In particular, Evolve users can access GPUs within TensorFlow for accelerating tasks such as training and inference. GPUs can also be leveraged within Spark in order to accelerate ETL applications, which are extract, transform, and load operations that are used to create the raw input data that is subsequently used in training phases. Lastly, Evolve also allows the users to accelerate inference models with the help of FPGAs within Python through the use of a custom interface developed by them. Now we're going to see each of these accelerated options, how exactly they are implemented and leveraged within Evolve. Regarding GPU acceleration in TensorFlow, TensorFlow provides on its own a GPU-enabled version. The software requirements for TensorFlow to run on GPU is an environment that has Python version greater than 2.7 installed, as well as installations of NVIDIA GPU drivers, CUDA, and cuDNN libraries. If these requirements are satisfied, TensorFlow code runs transparently by default on a single GPU rather than on CPU. In fact, if the user wants to execute something on CPU, he has to state this explicitly. Various operations available in TensorFlow have built-in CUDA implementations, and such operations are matrix multiplication, convolutions, pooling and activation functions, loss functions, optimizers, as well as training and prediction operations. Furthermore, the user can enable optimization features such as handling GPU memory and enabling multi-GPU execution for further boosting the performance. In the case of Spark, GPU support can help to parallelize and accelerate data processing queries of the ETL phase, which performs queries on on big datasets and prepares raw input data for the learning phase. The component that enables the integration of GPU over Spark version 3 is Rapids, which is a plugin that provides GPU parallelism and high bandwidth memory speed. Now within Spark SQL and data frames can use the provided libraries for GPU acceleration for columnar data processing and query plans. Rapids also provides a new SAFL implementation, which is built upon OpenUCX communication libraries that leverage NVLink, RDMA, and InfiniBand, so that they can dramatically decrease the data transfer among Spark processes. Lastly, for Fpga acceleration, Evolve allows the users to leverage pre-trained inference models and map them to pre-trained Fpga accelerators. For that purpose, within Python, the users can download pre-trained models from libraries such as Keras. In Evolve, we have a library with Fpga accelerators for AlexNet, VGG16, and ResNet 50. The users can save locally the weights of these pre-trained models and then use them to configure the pre-built Fpga accelerators, which have been optimized so that they can run with the most efficient manner on the Fpga device available on the platform. Access to these acceleration capabilities are exposed to the Evolve platform through the resource manager selected, which is Kubernetes. Kubernetes is an open source system deployed on top of a cluster of nodes and responsible for orchestrating, scheduling, and in general managing containerized applications. Containers are very similar to virtual machines. They package code and all the dependencies, the software dependencies that are required for this code to execute. And as those are defined by Docker container image. Once the Docker container is deployed, it can run reliably over any different environment. Kubernetes now handles the execution of these containers as these are requested by the users and decides on which node of the cluster this will be deployed. In order to expose FPGAs and GPUs to Kubernetes, we first have to build the Docker images with support for FPGA and GPUs. The Docker images we have created support both development and deployment phases so that users can both develop and run applications within these containers. For the FPGA Docker image, we have installed an Intel SDK for OpenCL for development purposes, and also the Intel runtime for FPGA execution. FPGA applications can be run either command line or within Python, with the additional overhead of the user building a custom interface for calling the accelerator. When the Evolve user asks for the execution of an FPGA application, Kubernetes is notified accordingly so that this application is scheduled to run on the node that is connected with the FPGA. Similarly, the GPU Docker image is equipped with the necessary CUDA and NVIDIA drivers, and depending on the application, it is furthermore equipped with TensorFlow with GPU or Spark with Rapids. An NVIDIA plugin in Kubernetes is installed so that the respective applications that target GPUs can be scheduled on the GPU nodes. Lastly, in order to further facilitate the experience of the Evolve user, Evolve has created the user interface dashboard, which is called CarveDash, and it is developed in order to allow users to easily configure and start various services. The user interface is based on Zeppelin notebooks that run as a container with Kubernetes instead. This dashboard provides multiple available templates for Zeppelin notebooks, each one with support for a different feature of the platform. For example, there are notebooks that support the use of FPGA, the use of GPUs, TensorFlow with GPUs, or Spark with GPU support. Special Docker images have been created that include and build upon the previous ones created for FPGA and GPU support and are further enhanced with support for Zeppelin. Therefore, the user connects on the user interface on dashboard, selects the desired notebook based on the application he wants to run, and Kubernetes decides on which node of the cluster this will be deployed. So this concludes the theoretical part of this presentation. Next, we're going to showcase 2 video recordings that demonstrate exactly how this dashboard can be utilized and access GPUs and FPGAs. The one use case demonstrates the use of Spark version 3 with Rapids. It focuses on an ETL application that performs analytics to a dataset derived from Fannie Mae's single-family loan performance data. In order to highlight the benefits of GPU acceleration, we first execute the application using a single executor in Spark on CPU only, and then on a configuration that involves both CPU and GPU. Next, we examine the scaling of the performance when utilizing multiple executors and provide the respective comparative analysis. For exhibiting and showcasing the use of FPGAs, we have selected the image classification application that uses the VGG16 inference model. In summary, this example imports a TensorFlow pre-built, pre-trained model for this CNN network. And the user can configure a pre-built CNN accelerator for VGG16 using the weights and biases of this model. The performance of this accelerator is then compared with the CPU. Now, regarding the creation and use of the specific accelerator, it is developed offline in OpenCL. In Evolve, we have adopted an open source library called PipeCNN, which includes accelerators written in OpenCL for 3 very popular CNN architectures, VGG16, AlexNet, and ResNet. These networks are built for the FPGA using the Intel FPGA SDK, following a typical process for building accelerators for FPGAs, which is the synthesis, placement, and routing procedures. The accelerators created are optimized for execution on the Stratix 10 device available on the Evolve platform, and the result is a bitstream that configures the FPGA with the accelerator. This bitstream is followingly wrapped in a dynamically linked library along with the interface written in OpenCL that calls the accelerator. This library, which is in the form of a shared object, can then be imported in Python and utilized by any Evolve user. On the runtime, the Evolve user only has to call this library and configure the FPGA and pass the input for classification. So moving forward, we're going to deploy we're going to show you a video of this FPGA use in the dashboard. Hopefully now you're seeing video. We can see the view of the dashboard. We have already opened the notebook that has access to the FPGA device. Each paragraph is a stage of the workflow described before. So the first paragraph simply copies some data that are required on the working directory. Data as such are the bitstream of the FPGA, as well as the dynamically linked library, which is, as we can see, a shared object. In the next paragraph, the user can install TensorFlow and any other software requirements, for example, Matplotlib for illustrating later on the image for classification, as well as the results. Once this is completed, we make sure that the FPGA is ready to use, and we make sure that the kernel can see the FPGA device and that it is mounted. On the next part, we move on the Python part of the application. As a first step, the user can download the pre-trained model from TensorFlow Keras and save it on the working directory. This can take a while since the model is very complex, and we print the summary of the layers to make sure that this is the model we want to execute. After having saved the model, we then move on to process the weights and biases of this model. We perform a quantization of the weights and save them in binary format, which is required by the Fpga accelerator. This takes several minutes, therefore it has been conducted offline. So we move on immediately to the next part, which is preparing the image for use in Fpga. For that purpose, we use OpenCV library. We change the scaling and transform the image to fixed point, and again, we save it in binary format. We can see that the image we want to classify is the image of a kitten. Then we move on to the part of actually running the inference on the Fpga. For that purpose, in Python, we import the shared object as a dynamically linked library. This object contains the interface to call with the OpenCL function calls to configure the Fpga and call the accelerator. We pass as arguments the input file as well as the weights that we have previously extracted. We can see on the terminal that the model is being executed layer by layer. And the classification result is that the image is that of a kid fox. In the next paragraph, we're going to repeat the same process, this time on CPU. Again, we use TensorFlow. We save the pre-trained model for VGG16. We pre-process again the image for use by this model and run the predict by using the built-in TensorFlow predict method. After having displayed the model, we see that the classification result is the same. It is also a kid fox. Now, we have retained the execution times for each of these cases, and we demonstrate that, in fact, Fpga execution of inference can deliver speed up to 8 in respect with the CPU implementation of TensorFlow. So this was the example of how to use FPGAs on the Evolve dashboard. Now we're going to move on to the next demonstration of the Spark application. This will be conducted by Angelos, which is also a colleague on ICCS team.
Hello, everyone. Let me share my screen. Okay, in this demo, we present an ETL example that performs data preparation and feature engineering on a 5 GB subset of Animaze dataset. For each Spark application, we have to define a paragraph that specifies the way our application is going to run. In our case, we define that one executor that consumes 16 GB of memory is going to be executed on an S65 node. This paragraph contains the code of our application. In particular, it contains the SQL queries and some utility functions. After executing this paragraph, we can see in the terminal that one executor was created. This application is divided in 2 stages. We first convert the input CSV data to Parquet format and then execute the query. We convert the input data to Apache Parquet format for compression purposes in order to decrease the data we have to load. Furthermore, Apache Parquet is a columnar format, meaning that it stores the data of each column separately. In this way, we decrease the data we have to read for example, in an SQL query, as we only need to read the columns that we care about. Let's execute the conversion. This paragraph takes about 8 minutes and 45 seconds, and then we execute the query, which takes about 25 minutes and 33 seconds. In this notebook, we demonstrate the exact same application with GPU configuration. As we can see from the configuration paragraph, we define that each executor is going to bind one NVIDIA GPU of an S65 node. We also provide parameters for Rapids, the plugin that enables GPU acceleration. For example, concurrent GPU tasks parameter specifies that at each time only one GPU accelerated task will be enabled. It should be noted that the code is exactly the same. This is one of the major advantages of Spark 3 with Rapids plugin, as we do not have to modify our code in order to leverage the benefits of GPU acceleration. Let's start by converting the input CSV data to Apache Parquet format, as we previously did. As we can see from NVIDIA SMI tool, the created pod binded one of the Tesla P40 GPUs of an S65 node and is executing tasks. We can verify that the pod is executing tasks by the allocated memory, the GPU utilization percentage that increases, and finally, the power consumption. This paragraph takes about 1 minute and 21 seconds. Then we execute the query. Which takes about 9 minutes and 3 seconds. And finally, we plot the output data. As we can see, Spark 3 with Rapids plugin leads to significant speedups for both operations. We can increase the number of executors by simply increasing the executor instances on the configuration paragraph. In this way, we can further leverage the acceleration capabilities of Evolve's platform. After executing both of these paragraphs, we can see in the terminal through kubectl command that two pods are created, two executors are created on two different nodes of our cluster. As Konstantina mentioned, we executed an experiment where we increased the number of executors for CPU only and CPU with GPU execution and measured the overall execution time of the aforementioned code. As the figure depicts, Spark 3 with Rapids plugin leads to smaller execution time for all the examined executors. We can also observe that for one executor, Spark 3 with Rapids plugin leads to similar execution time with the CPU-only execution with 4 executors. This observation showcases that Spark 3 with Rapids plugin leads to resources savings in a cluster level. And this concludes the ETL demo. Thank you very much.
Okay, thank you very much. Is there any part of the demo still to be done?
No, we're finished with the demonstrations.
Good. So thank you very much, Konstantina. And then I see that there is only one question. I suggest that we share the answers of these questions. I will answer this question first. So I said it out loud. The question is from Manos Pavlidakis, and the question is there any performance gain when running image classifications to FPGA compared to GPU? This is the first part of the question. Second part is what happens if the FPGA needs to be reconfigured to run another bit stream? So the first part is that when maybe I put it again, I don't know if I can put it again, my screen. No, I have some trouble to. Okay, so I can answer this question. We are really displaying again the table. So it's not about an application of CNN about image classification or image reconnection or something like that. It's about first of all the characteristics of the artificial neural networks, or more precisely in that case for the image classification, the CNN, the convolutional neural networks. It's about the topologies, the complexities, the size of this kind of NN, which can have impact on the performance either on FPGA or GPU. So we cannot just answer about the impacts on the image classification. In my previous presentations of the results, I already show that for small, for example, in that case, for small CNN like AlexNet, for example, FPGA sounds to be a little bit better than GPUs, but it's not always the case. And for the other, a little bit larger CNN like RaceNet or UGG16 or more than this, obviously sounds that GPUs is better. So it depends a lot on the characteristic of the CNN user for these functionalities. We cannot conclude for only for one functionalities of the CNN. First point, and the second point is that obviously when you use FPGA, one of the bottlenecks, bad impacts on the use of FPGAs about the transfer of data when you use OpenCL, obviously, between the host and the FPGA and back, the results back. It was a lot of times in this kind of transfer of data, and that we try to avoid the transfer data between the accelerators and the host. And most of the times, all the kernels are loaded, programmed in FPGA, and we won't change at least for some instances or sequence of inference of instance. We won't reprogram the FPGA. Obviously, it takes a lot of time, even if it's only a second for FPGA to reprogram the FPGA. Even dynamically, we want to reprogram dynamically the FPGAs because it takes a lot of time to reset, to reconnect the clocks, to reinitialize the PLL, stuff like that, which can be error prone too. So most of the time, we won't try to reconfigure the FPGA with another bit streams in between. That is things which, at least from my point of view, stay stable in this part. So I don't know if I answered your question or not, but maybe Konstantina, you can comment a little bit about the experiences we have had with the Thales pilots with FPGA compared to GPUs. Konstantina?
Yes, hello, thank you, Nam. What I can add on this account is that I have conducted some experiments for two of the aforementioned models. I think it was VGG16 and ResNet. And I did see some speed up of the FPGAs over implementations similar on the GPUs within TensorFlow. So I have some speed up around ×3 faster the FPGAs could be. Of course, the overhead of development or even calling an FPGA accelerator is greater than that of the GPU. So in general, I think that it is easier for most applications in training and inference to be accelerated with GPUs. Now, regarding reconfiguration, in the example we demonstrated on the dashboard, the user will have to reconfigure the Fpga, and the accelerator that was previously running on the Fpga will be erased. So there's not some feature for partial reconfiguration, if this is what the question was aiming at. So I think that's all.
I have another question. I think it is for you, Konstantina, from some anonymous persons. What amount of resources in terms of CPUs and memory are allocated per executors in this demo?
I think that this question is for the ETL demo.
Okay, go ahead, please.
Yes, each executor allocated 1 core and 16 gigabytes of memory. So.
Okay.
Yes.
Just 16 gigabytes of memory. Do you have any information about the occupation ratios of the memory?
Sorry, I did not understand.
Do you have any information about the occupation ratios of the memories? You say 16 gigabytes. Do you use it in the whole memories, or?
Actually, the executor uses all of this data. If we decrease the amount of data, the container fails. So,
okay.
So it consumes all of the available memory.
Thank you very much. Thank you.
Thank you.
Yeah. So I don't see any other questions. Therefore, I think that we can stop the webinar today here. And I would like to thank you, first of all the presenters in this webinar, Konstantina Angelos, and then thank you for all the audience for your participation, and wish you a very nice day.
Thank you very much.
Thank you.
Everyone for listening.
Bye-bye.